My daytime job is at NetInsight in Stockholm. We make networking stuff like these machines or these, and then we connect them in networks. I have absolutely no idea how many CPUs are in this picture, because for every plug-in board there is at least 2 CPUs and at least 1 FPGA. And we make everything from the mechanics up to the network management systems. So it's, that is full stack, isn't it? We also do some cloud-based video streaming software, which I haven't tried to make any pictures of. But back on topic, Asynchronous I. I've written this talk primarily out of curiosity. I've been working with networking for a long time, but I have not used IOU ring. And I'm curious about coroutines, so I wanted to dive in and see what can this do. And I'm afraid, after having written this talk, I'm slightly less enthusiastic than I was when I wrote the abstract for it, which you may notice. So, Linux networking. Traditionally, we use select or poll or epoll to register file descriptors that we want to react to. And then when we get a notification that there is data to read, we can use read or receive message, receive multi-message on Linux to read the data. Or the same thing to send, we get information from select or poll or epoll that file descriptor is ready to write to. And that is fine, it works. So you typically end up with something looking more or less like this. You have a poller that you can subscribe to a file descriptor, something like this add function here, where you say, when data arrives on this file descriptor, call me. So you store this information, and then you have a wait function that just waits for something to happen from poll, and when it does, you traverse all the file descriptors, read the data into a buffer, and then call the callback. I should mention this magic number, 1500. That is because I'm a very lazy person. Normally, when you do networking, you would have some kind of message memory buffer or something, but that I don't want to have this in a presentation because it just complicates matters so much. And I don't remember what the maximum size of the payload of a UDP packet is, so I just grabbed 1500 because it's enough. Slide away. So what happens then when you run this is you call poll, some data comes into the IP stack which fills a buffer in the kernel. You get released from poll, so you start reading where the data is copied. And then you get more packets filled into a kernel space buffer, and this happens in parallel while you're processing the data that you just copied into your buffer. And then you call a new poll, etc. So we can just show what happens when you do this. So I have a very simple program here with, here's a poller that I just showed you, and I have 2 simple callbacks, one that just counts the number of packets and sums the number of bytes in the packets, and one that prints the values, and then we're done. So one of them listens to port 4001 to port 4001 on localhost. It's a simple way to get things going. So I can use strace. Strace is an excellent debugging tool in Linux. Is this large enough? Can you read this? I don't really care if people in the front row are nodding. That doesn't count. So I can do like this. This is also another cool Linux thing, or actually it's a bash shell thing. It has a pseudo device for UDP ports. So I'm just echoing something to dev UDP localhost 4000, and then it makes a UDP packet of the data and sends it to that port. So if I do that, we see how data was read, and we can get another poll will stay there. We can do another one. We can do 1 to 4001 just to stop it, and then we see that it counted to 3 packets, and so on. Okay, nothing remarkable in any way. But this presentation was about asynchronous I/O and IOU ring, and it behaves a little bit different. IOU ring arrived in Linux kernel 5, I believe. And what the U-ring is it's a shared memory data structure. It's shared between the kernel and your user space process. And it's shared memory and lock-free, and it models 2 queues, a submission queue and a completion queue. And with this, you can do IP I/O and file system I/O. And I don't believe you can use any other file descriptors than those. And the way you do it, actually, you have 2 APIs for IOU ring. That is interesting. So one of them is the so-called high-level API, which I'm going to use, which is really not high-level. Void stars, just saying. But then you also have the low-level API, which basically is just a description of how this lock-free shared memory data structure works. And then it's up to you to not wreak too much havoc on the system. By the way, feel free to interrupt with questions at any moment. So the high-level API you get by including liburing. So this is a C API, of course. So you instantiate and initialize a U-ring. The size is the maximum number of pending requests that you can have. So it's the size of the submission and completion queue. And this must be known at init time. You cannot grow it at any time. And what you do when you want something to happen is you get a submission queue entry and you prepare an operation. In this case, you prepare a read. So you say, I want you to be ready to read data for this entry, for this file descriptor, and when data arrives, I want you to fill it to this data area that is pointed to by the PTR and size. And the 0 at the end is just a flag that we can ignore right now. And then we can associate this entry with some kind of work so that when we get a completion for the entry, we can find whatever it was we wanted to do, because we may not want to do the same thing for every single packet that arrives, always. 64 bits is definitely enough. You may need to do some indirection to model your data, because you cannot associate both a function and an object in 64 bits alone, but it's not a big deal. And then when you're waiting for data, you wait for a completion queue entry on the ring. So you typically write, well, I wouldn't say typically, you can write something like this that is modeled fairly closely to the poller I showed earlier, where we can add work to a file descriptor and we can wait. But there is a difference in the implementation, because I need now, I cannot defer having this 1500 bytes buffer to read into until after things are done, because this is a shared memory thing. It needs to know where to store things. So I have this internal structure read work that contains the callback and the file descriptor and the buffer. So when we add something, we get a new work that we store the callback and file descriptor in, get a new submission queue entry, and prepare the read. And by the way, when I say prepare read, this is an incredibly cheap operation. This is just direct access into an array. There are no system calls here. So it just writes into this shared memory data structure. Yeah, someone already prepared all those things I said. That's very nice. Cool. So what happens when you run these is that you have a number of data buffers that are ready. And the data arrives and filled in from the kernel while we're waiting. When the data is filled into our buffer that we actually gave it when it said prepare read. When it's done, it starts filling in the next buffer while we process the data that we just received. And then the kernel starts filling the next one while we process the previous one. So we essentially get multi-threading and zero copy. This is nice. For the silly example I showed you where I just sent a few bytes here and there, this doesn't absolutely not matter at all. But as I said a little bit jokingly while we were waiting for the online thing to come on, I worked a bit with video streaming software. And when each video stream is maybe 10 megabytes per second, and you have 50, 60 of these at the same time, saving a copy for each does lower the pressure on the caches quite substantially. So this is a big thing. And there are fewer system calls too, which I'm going to show you. So let's have a look. So just to look at the sources, we have the ring that I just showed you. I didn't show you the weight, how that happens. So we submit to the U ring on weight because then we initiate a system call here. And then we wait for data. If there is already data available, we just get it. And then call if it worked, if the error code is 0, we call the completion queue entry lambda that I have here, which just calls a callback. If the callback said everything was okay, then we prepare the next read. Yes?
Question. Is this waiting for the next data? Is this waiting on a condition variable, or how is this done?
I actually don't know how it's implemented. I really don't know how it's implemented. Condition variable seems like it could be. Yeah, I don't know. So, and then we have the main here that is basically the same. The difference here is that now I'm registered this calculate sum 4 times. So I have a U ring that can take care of now up to 4 received packages for calc sum in flight at the same time. So let's see how this actually works if I try to. So now we see that it calls uring enter. So when we first, after having done all these prepare reads, I would say, okay, go. And then we call, call to get a completion entry, but there is none available, so therefore it becomes a second system call. So we can do this again, and this is quite unexciting because we still get 2 system calls per request, per packet. But let's go a little while. Instead of just strace, we can use strace-c. Their c doesn't show every single system call, it just counts them. How many system calls of each kind do we have? And then we can use another really good Linux, maybe it's not just Linux, I'm not sure, networking debugging tool, nping. So with nping, I can say, well, -q, be quiet, don't say anything. Send UDP packets to port 4000. Rate 1000 is interesting. When you give a rate that is less than 1000, that means the number of packets per second. When you say 1000, it just goes full speed, as fast as it possibly can. 20,000 packets of length 1400. So let's go. We dropped some packets, 7,400, okay. But the interesting thing is 14,900. So we have basically 2 system calls per packet received. Let's do the same with uring. We did not drop any packets. Don't draw too many conclusions on this, because what this is measuring basically the overhead of strace, which is substantial. So uring is good, but it's not that good. But what is interesting is to see that for 20,000 packets received, we have a little more than 5,000 system calls. That is a lot cheaper. System calls are not cheap. And we also have, as I mentioned, since it's a shared memory structure, we have less copying of data. So we are leaner on the caches as well. So this is good. So, coroutines. Change of topic, but we'll merge them together in a while. So coroutines offers a way for you to write asynchronous code as if they were continuous loops. We have language support from C++20, and compiler magic converts it to something else via types that you must write. And those types are mind-bogglingly hard to understand, unfortunately. And the standard library isn't of much help, unfortunately. Here comes the whining, okay? So what happens is, here we have 2 coroutines, the right and the left. So we can have the first one, the one on the right, suspended, just waiting for something to happen. The one on the left is computing some value x. And then it suspends its execution, hands it over to the right-hand side, which can be resumed with this value x, do something with it. And when it's done, it suspends its execution, hands everything back to the one on the left, computes another x, suspends its execution, hands over, right, left, right, okay. Hands over execution to the right, which works with x, suspends, etc. Go on. You see the idea. And what happens then is you can write a coroutine like this, my corow, and we have this while loop. We co-await a source to get a value a, and we do something with it. And we create a corow object by calling my corow with some values and a source of data. And what the compiler does when it sees this, since co-await and co-return, they tell the compiler, this is a coroutine. So it transmogrifies it into something sort of kind of like this. It creates a coroutine object where the local variables in the coroutine, x and y and result, becomes member variables in the coroutine object. And this loop, this while loop, actually becomes part of, as if you had an operator function call that gives it values and you do the work in that. And then when you have this call to get my coroutine object by calling it, the compiler wraps this. It allocates the coroutine object and some extra code and data that is used to administer all this. And this is a vast oversimplification, but it's as a first step, as a mental model to get you to grasp roughly what actually happens with the coroutine. This is probably okay enough to get you going. Since we don't actually have much support from the standard library to speak of, it means that this coroutine type is one that we must write. Or if you're lucky enough to find an open source library that you can use, by all means. And also this coroutine source that we co-await values from, you have to write this one yourself. So most blogs and articles and conference videos, etc., that I've seen about coroutines refer to these as tasks. So I will not add to the confusion by using a different name. I'm sticking to task. A task must have a promise type, and no, it is not std promise. It is absolutely not std promise. And yeah, we have to write the promise type also. We'll get there. And since I want this task to be co-awaitable, we must have an operator co-await. And this promise, like I showed, it is allocated by the compiler-generated code, so it's magic that happens there. And it is handed over to the task. And we must keep track of it, keep track of its lifetime. And we must destroy it the right way. Calling delete on this is a really, really, really bad idea. Ask me how I know. So what you do is you create, well, what I choose to do is I create a coroutine deleter, which, when called with a promise, it calls this coroutine handle, from promise, to get a handle that we can call destroy on, and then it's destroyed the correct way with all this extra compiler magic generated craft that was added to this code. Simple enough, eh? So then we get to the promise, which is not a std promise, where there is a lot of, I feel that there's a lot of ritualistic code here. We must just follow this ritual. So you must have a function get return object. That is actually the one that creates the task from the promise that has been allocated. We have initial suspend and final suspend, which typically don't have any function bodies at all. They, other than just to return a default constructed value of their return type. The return types are suspend never and suspend always, which I guess kind of indicates what they're about. So when the object is created, it calls initial suspend, and if it says suspend never, then it continues executing. If it says suspend always, then we're done there, and continue with something else. Here are some extra helper functions. These are not absolutely necessary. And here we store, for the promise, we store a continuation. So when the coroutine is suspended, we store that coroutine as the continuation, so that when the other one is done with its work and want to wake this one up again, it can say, this is the one to continue with. Good. You may now get the idea that you don't actually have to put this in the promise type. You can have these continuations elsewhere in some cooperative scheduler. I'm sure people will do that. I'm also sure people will create messes of that, but it can probably be really cool if you know what you're doing. So we need to be able to put values into our promise, because that's the thing. It's meant to communicate. So it's empty, we give it a value, then we can wake up the one that is waiting so it can get the value, etc. So I'm storing everything in an optional, which is strictly speaking not good enough. But for now. So when we I call this function yield value, we give it something and then we just place into this optional the value, and we resume the one that was waiting on this future. The reason why I said that this is not enough is the function just above this unhandled exception. I have completely ignored exceptions in this. So if bad things happens, then bad things really happens, because I'm just ignoring this completely. Was there a question? Oh, okay. And then also, if we want it to be co-awaitable, we have this co-await operator that returns unawaitable, which also needs to have a lot of code like this. Await ready to ask, do you have data for me? And await suspend, where we said, okay, you didn't have data, so then I'm suspending, so then we store the next function, the next coroutine. And promise get to get the value back. So yeah, a lot of code that doesn't do much, it feels like. But let's have a look, because there's actually a lot of things happening. So we can go past these. We have the promise type. It looks the same if we ignore these trace things. Oh, damn it. I hope no one was hurt because I hit you in the face. I'm using these traces just to be able to show you what is happening. But what I have a new thing on task that I haven't showed you. I have a static member make that it just does co-await suspend always, and we get a handle that is suspended, but that we can then use for things. So I have a coroutine print all that just reads data, awaits data from this values member here, values parameter. So this loop now becomes a coroutine object that lives on the heap, and it gets called with new values v as the coroutine is called or is resumed. So I make an incoming task. I get a coroutine for the print all from the incoming ones. I get the promise, and I call yield value on the promise. Wrong one. And now it's a lot of things happening. So when we call this line incoming make, we see it first creates the promise and then calls the get return object so that a task can be created. Calls initial suspend, which suspends, which means that execution continues on the next line, which is print all, which calls the printer task to be created. Its initial suspend is called. Its initial suspend was return suspend never, so it continues its execution. This trace print all calls co-await, which calls await ready on the incoming. It says no, I don't have any value, so it is suspended. We go back here where I yield values. Yield value calls await resume, which calls get, and we get the value and print it, and round and round it goes. A lot of work. But that is the way this happens. So you have this communication between our coroutine code, the task, and the promise, and the awaitable, and they're all chatting via the promise to ensure the correct flow of information and execution. So let's make a simple computation pipeline. So a filter is good to have. Something that takes a predicate and some awaitable task. We're looping over values. When we find something we want, we co-yield it. So co-yield calls the yield value member function of the promise of the return type from this function. So it wasn't a completely arbitrary choice that I called this function yield value, because this is what the language does for you. One thing to note here is this asymmetry. It is perfectly okay for there to not be a very strong relation between the number of times we co-await values and the number of times we co-yield values. So this is a filter. It may not actually call co-yield at all. Or we could have one that duplicates values and co-yields every value twice or something. So you don't just have to take one value in, massage it, and pass it on. Okay, so we can write something like this, where we create a filter, odd values are filter in of incoming from is odd, and then we have our printer that prints all values from odd values. And then we just loop and call yield value on a number of, on a range, like this. So we can show this. So here we have, I moved the task into a header now just to not have to repeat this all the time. Print everything, print all, and our filter in exactly as I showed you, and this simple loop as I showed you. And when we run this, we see that we got indeed the odd values. All right. So let's put these together. U-ring and coroutines. So we have already seen how IO-U-ring offers asynchronous data, and it does it also without copying. And we've seen how yield value on a coroutine promise pushes data through a computation pipeline, or a coroutine pipeline. And we have seen how to read values from a coroutine, awaitable with co-await, and how to forward values downstream with co-yield. So it feels like it should be possible to merge these ideas, right? So let's do that. So here's a little helper that is strictly not necessary, but it just shortens the code a little bit. So when this lambda, when called with a promise, it returns another lambda that just calls yield value with whatever it is called with. So we can go back to this function that we had, this program that we had. So we can get a count packet coroutine that takes an awaitable task. And it can look like this. We have the packets and bytes as references, and we just co-await packets, increments the counters, and pass the packet on to the next coroutine. And then one that converts this span of char to strings, because that's what I want to do. So just, again, a loop that co-awaits. This is a task of span of char, so it gets a span of char. That is a packet, and it co-yields a string that is created from these. And I want to strip trailing new lines from this, because why not? And then I want to concatenate the strings received up until I get 40 characters long strings. And now we have something a little bit different here, because we have the current line at the top, which, if you remember, a local variable in a coroutine becomes a member variable of the coroutine object. So this is a coroutine that has and changes its state every time it gets some new data. So in here, the first if, we check if the string we just received, if adding it to the current line would be too long, then we yield what we had and store what we got. Otherwise, we just append. All right? And then print lines, that just another coroutine that just prints. I set colon delimiter just to make it a little bit easier to see where things are, and a new line. So what we do then is just this add port 4000 with a toPromise, this helper that just calls the yield value function on the promise to make things happen in the pipeline. So we can look at this. So yeah, count packets and toString exactly as I showed you. It's concatenate to print lines, etc. So yeah, that's the one. And we get data from several of these. So now I'm just getting nonsense strings by reading /dev and sending the names of my devices. Is that a security leak? To port 4000. And we see how the names are added up until a length of 40, and then we print them. So, and then we can do this 4001 just to exit the program. Okay, that works. But this is horrible code. Keeping all these coroutine objects alive, and trust me, you need to keep them alive. You will get extremely confusing and frustrating bug hunting if you don't do, because then you're calling functions on dead objects. That is not good. So you need to keep all these alive, and that is horrible. So even though it is powerful to be able to write all these computation steps as if they were loops, but this mess is not nice, I think. So can we do better? So let's reduce the number of references that we need to take care of. So we can take the task by value, then we don't have to store the awaitable task that we had. The same with our print all, stored by value. And then we can write code like this, where we call filter in with this odd, and we move the incoming, and the return type, the coroutine object from filter in, is just passed in as an R value into print all, where it's kept as as a variable. Like that. So, I mean, it's still not great, but there are fewer objects to keep alive. So it's progress. It's not great, but it's progress. So what can we do? We can add another level of indirection. So I make filter in a higher order function that returns a lambda that holds the predicate as a member. Now, I've been told, actually, at one point by another conference presenter that lambdas cannot be coroutines. That is incorrect. Lambdas can be coroutines. But I think the reason that that person thought you couldn't is that you now have two objects that you have to be aware of that they refer to the same thing. So you have the lambda itself is an object with its member functions. And now the return value from the lambda is a coroutine object that lives on the heap and calls this code in the lambda, which expects also the lambda object to be alive. If you have moved one of these, bad things will happen. So I think that's where the misunderstanding comes from. So you can do this, but you have to be really, really, really careful about object lifetime. And we need to be explicit about the return type from the lambda. Because automatic type deduction doesn't work, because it knows it must be some coroutine type, but which I can have modeled several with different behaviors. Then we do the same with print all, that just captures the stream. So now I can write that my pipeline is to see out and filter in of is odd, which is still not great. But we're getting there. I promise you, we are getting there. Boy, am I getting ahead of myself. We're going to be done very early, which is maybe good because we started late. So I added a little helper. Coro stage is just a struct that inherits from whatever it's instantiated with. And we have a deduction guideline to make sure that if I'm constructing a Coro stage from an object of some type, then it is a Coro stage of that type that we instantiate. And in this case, I'm using Coro stage for my functions for my lambdas that has a function call operator, which means that the function call operator of the lambda is inherited by the Coro stage. So I have it there. And then we create a pipe operator because pipe operators are cool. And they are. It takes Coro stages by value, and it returns a lambda that captures the two coroutine stages, Coro stages. And when it is called, it calls the right hand with the right result of the left hand with the result of whatever it was called with. And then we ensure that we capture by move, because these will be move-only objects, because my coroutine task types holds the promise by unique pointer. So they are not copyable. And then I wrap it in a Coro stage so that we can call several pipes after each other, just creating bigger and bigger and bigger Coro stage objects. So very small change, just wrap or filter in. The same with print all, just wrap it. And now we can write this. This is actually good. I think. This is quite readable. We want to filter something that it is odd and pass it on to print all to stand out. This is good. So let's actually have a look at this. You're awfully quiet. Am I so clear or am I so confusing? So never mind these. Yeah. We have the pipe operator that I showed you, and the chorus stage, and the tasks, etc. Filter in, and this pipeline. And of course this works, exactly the same as before. So, good. So we're on to something. We should be able to do something good here, I think. So how do I get data from the U-ring into our pipeline then? One problem is that the way okay, that's a bug on the slide. It's polar. It shouldn't be. It's ring. Okay, it should be ring. Close ring. Never mind. The problem is that we have this worker callback is a stud function. And stud function requires that whatever it is given, its type T, must be copyable. And I just said that our chorus stage objects are move only because we will hold unique pointers. So bummer. Right, but we have move only function. That is cool. We can use that instead. Anyone have a time machine? I wrote my own. It's super naive, but it works. And with that, we can use move only function instead. And then we can go on. So then we have the next problem. How do we create something that is callable from a span of char that feeds into a pipeline via a task of span of char? And I came up with this pretty darn horrendous construction. And the reason this is so horrendous is that I had a solution that was very simple, very elegant, very easy to understand, and dead wrong, as I discovered on Wednesday evening. So I panicked a little bit. And I wrote this horrible thing, which I'm not very proud of, but it works. It does its thing. So when called, we create a task object, get its promise, get the type. We return a lambda that just, really its only purpose is to have these objects, the task, the pipeline and the input task. And I had to resort to save the resulting coroutine as a unique pointer, which is absolutely horrible. And we then instantiate this coroutine handle on the first call, which is just so bad. And then on every call, yield the value to the promise. So this works, and I am really not proud of this code. I'm sure this can be done a lot better. But like I said, I may have panicked a little bit and just tossed something together that worked. But as horrible as that implementation is, we can now write this. Add to the ring the file descriptor for the UDP port 4000 on localhost, something that counts data, pipes to toString, pipes to strip trailing new line, pipes to concatenate to, pipes to print lines. I like this code. This is easy to understand what is happening. This is easy to read. I think this is really nice. So, gory implementation guts aside, the end result is pretty. So let's have a look. So now we have changed these to all be higher order functions that returns chorus stages. I even changed concatenate to take a length by value instead of being a template parameter. And print lines take the output stream. And then we have the horrible init task and this code. And it works. I like this. I really do like this. So, what can we conclude from this, though? Coroutines can be cool, and they are powerful. There is absolutely no doubt about that. Lack of a good library is a major pain. Writing one is not easy. It really isn't easy. I totally ignored cancellation here. Cancellation is tough stuff, both for coroutines and for IOU ring for completely different reasons. So for coroutines, you have these pending operations in this shared memory data structure that is mutated by the kernel outside of your control. You cannot just remove the objects. That will be bad, because then the kernel will write to wherever. So you have to take care of these. And coroutines cancellations are, well, the easy way to cancel them is to implement the stuff that I didn't with exceptions, because then the coroutine chain sort of just dies. But normally you don't want to implement normal control flow with exceptions. So you have to think a little bit about it. There are several ways to do it, but it's not straightforward. You have to be a bit careful. And it's extra tricky if you want to propagate backwards. So if it's if there's a coroutine far back in the chain that discovers an exit criteria and wants to propagate up to say, stop, I don't want more data, stop, stop, stop. Because we don't have that bidirectional channel easily. It is doable, but it's definitely not easy. Another thing that I haven't really showed you is that I said that there is a lot of ritualistic code where you have to write these sometimes completely empty functions that just return a default constructed value of an empty struct. The compiler looks at what functions do you have in your types and which signatures do they have. And it can generate completely different code depending on these. One interesting effect of this is when you try to learn about how coroutines work and you read blog posts, etc., and you see that everybody does them completely differently. So in the beginning, it's very confusing to understand why does this person write them this way and that person write them that way, and they're doing sort of the same thing. What's going on here? And there is a lot of possibilities to parameterize how they behave. So for example, where the coroutine object, where is it allocated? I ignored that completely. I just said it's allocated with operator new on the heap. But you can control these things. And even that thing I showed you about where I stored the continuation in the promise. Depending on how you write them, you may not need to do that. So this is very confusing when you're trying to learn about this. So this example was, I started writing saying it was simple, but it's not, it's simplistic. And I think we really need a good library, and we don't have one, and writing one is really, really, really hard. And I want to say that normally when I do a presentation where I have a lot of source code, I usually upload it to GitHub for people to look at. I'm not doing that with this one, because I fear that someone will not listen to what I say now. That is crap code. And they will download it and use it, and I will feel really bad about it. So I'm not going to upload it. Another takeaway is that when you're writing the library, when you're writing the coroutine types, the debugging experience is so bad. It's laughably bad. Especially when you get lifetime issues, which I got several times. So actually what I did, I'm not proud of this, but this is the way to do it, I think, I'm afraid. So this is a const expert string class, a very, very simple one, that can be used as a non-type template parameter. So my promises actually had this extra name as a template parameter, so that I can trace them and see not only is it a task of int or whatever, it's actually a task of int for print all that died, or whatever. And I can see that, okay, I got to this function and it called that, which is dead, okay, whatever. So you use these ones, like these names, so to propagate them, which feels 1980s, I think. I mean, this is just horrible, but it works. It helps. This is how I solved the majority of the bugs I had when writing on this, which is just terrible. But writing asynchronous code as if there were local loops is so convenient. It's so powerful. It makes life so much easier. And by being able to connect pipelines, you get really great support for generic utilities, like you want filter, probably. You want counters, probably, whatever. And they are completely generic. They will work with any type. You just use them. That is cool. Looking a bit at resources for further study. If you want to get into the IOU ring on Linux, Shoaib Hussein's Lord of the U-ring is a really good source. Very easy to, very accessible, easy to understand, good documentation. I recommend it strongly. For me, the key to grok, what's happening with coroutines, was Pavel Novikov's presentation, Understanding Coroutines by Example, given at C++ London in February 2021. So, Pavel, if you're looking, thank you. You saved me. Yeah, there used to be the next awesome coroutine library, CPB Coro. It's dead, as far as I know. Last time I looked, it was more than 2 years since the last commit. One thing that is definitely not dead, it's absolutely worth looking into, is libunifex. It uses coroutines and a sender-receiver pattern together with the IOU ring. I have not studied it enough to be able to say if it is good or not, but I trust many of the people who say that they like it. So by proxy, I like it, but I don't have a personal experience.
So you mentioned lifetime issues a few times. These were obvious bugs in the code, sort of using a reference after the end of after the lifetime of the object had expired.
I'm sorry, I don't think I understand what the question is.
Oh, well, it was more of an assertion. You found objects being used after they were destroyed, were you?
I'm saying that's it's an easy bug to make.
Yeah.
Unfortunately. Address sanitizer, UV sanitizer will find these for you. The message you get from them may not be the most friendly ever, but you will get the information.
Okay, so you were using those and they were helpful?
Yes.
Okay, did they miss anything?
If they did, they're still in the code.
Good answer. Okay. Thanks.
When you are doing a very complex pipeline with some of your coroutines that are allocating a lot of memory, isn't it a problem, like in terms of performances, to have a big pipeline of a lot of coroutines because you are jumping in memory back and forth, maybe making more cache misses or something?
It could be, but I think it's comparable to what you would get if you just change callbacks. I believe. I actually haven't measured. It is definitely, if your code is memory intensive rather than computation intensive, it is definitely faster than spreading it into threads, because communicating data across core caches is really expensive.
You'd crossed out the CPP Coro library there. What was the problem?
The problem with CPP Coro is that it's written for the Coroutines TS before Coroutines was standardized, and it hasn't been updated since. So that is the reason it's crossed over.
Yeah, but I may add to this that Louis Baker has published several blog posts about coroutines, and they are really worth to read. He explains the mechanics in very, very detail.
Yes.
So you were passing a span of characters out of the first coroutine, right? And then later on you were turning that into a string.
Yeah.
Where was that span of characters living?
In the ring implementation, I had this per entry. I had this 1500 bytes buffer, and from there I created the span with the length of the exact number of bytes that was received, and passed them into the coroutines.
Okay, but so isn't that buffer going out of scope when you pass it into the coroutine?
No, because good question. Very good question. I'm glad you asked that. No, it doesn't, because the original caller is still in scope. So it passes it to the coroutine, which passes it to the next coroutine, which passes it to the next coroutine, and then we trickle back.
I see. Yeah, that makes sense. Thank you.